Hey guys, in this video I'm going to go over how to perform a Pearson's chi-square test of association. So this is a test that you perform when you're doing categorical data analysis, and it's used to test the association of two categorical variables. In this video, I'm first going to go over how you perform the Pearson's chi-square test of association, and then I'm going to do an example at the end of the video. So for the chi-squared test of association, the null hypothesis is that there's no association between your two categorical variables. Then the alternative hypothesis is going to be that there is an association. Pearson's chi-squared test of association is usually tested on contingency tables, which are tables that show you the frequency distribution of your two categorical variables. So in this video, I'm going to do an example where I have two categorical variables and each variable has two factor levels. So let's say I have a categorical variable called b with two factor levels b1 and b2, and then I have another categorical variable a with two factor levels a1 and a2. So I want to test the association between the variable a and b. Then I would have a contingency table that looks like this. So this box here has the observed frequency counts for each distribution of level A and B. So A, lowercase a, refers to the observed frequency of having factor level A1 and B1. Lowercase b refers to the observed frequency of having factor level B1 and factor level A2. C refers to having B2 and A1, and D refers to having A2 and B2. So those are known as the observed frequency counts. Then the final row and the final column have the row sums and the column sums of the contingency table. These values here are the row sums of factor level B1 and B2. So A plus B is the row sum of having factor level B, or being in factor level B1, and then C plus D is the row sum of being in factor level B2. These values here are the column sums, so A plus C refers to having or being in factor level A1, and B plus D refers to being in factor level A2. And then finally, the bottom right cell is always the total sum. So this is always the total number of observations, or it's your sample size n. So that's how you read a contingency table, and then using this contingency table, you can write out the test statistic, which is a chi-squared test statistic. So I have pasted here the chi-squared test statistic that you use for a Pearson's chi-squared test of association. For this test statistic, OIJ refers to the observed frequency count for every ith row and jth column. EIJ refers to the expected frequency count of every ith row and jth column. And then capital I refers to the total number of factor levels in one of your categorical variables. So I'm going to refer to that as variable A, and then capital J refers to the total number of factor levels for your second categorical variable, which I'm going to call B. Then, when you calculate this test statistic to perform the test where you either reject or fail to reject your null hypothesis, you're going to compare that to a chi-squared critical value that has degrees of freedom equal to capital I minus 1 times capital J minus 1. And so this would be your chi-squared critical value that you test at a certain level of significance, which is known as the alpha level. Going back to the contingency table, we know that our lowercase a, b, c, d are our observed frequency counts OIJ. So when we do these tests of associations, we're going to be given usually lowercase a, b, c, d, which are our observed frequency counts. Now, to fill in the chi-square test statistic, we need to calculate the expected frequency counts for each combination of all your factor levels. So that's going to be EIJ, your expected frequency counts, and this is going to be equal to the row sum times the column sum divided by the total sum n. So I'm going to write that out as the row sum for every row times the column sum for every column divided by n. So you're going to have, for every observed frequency count, you're going to have a corresponding expected frequency count. So for A1, B1, there's an observed count and an expected count that you have to calculate. The same thing for A2, B1, and B2, A1, and B2, A2. So with all this information, we're now ready to do an example. So this is the example that I want to do in this video. I have a 2x2 contingency table of two categorical variables, gender and belief in afterlife. And so gender has two levels, female and male, and belief in afterlife is yes or no. So for this problem, I want to use the Pearson's chi-square test of association to test if there's an association between these two variables, gender and belief in afterlife. So I want to see if the belief in afterlife is dependent in some way on a person's gender. And I'm going to use the Pearson's chi-square test of association to test this hypothesis. So the null hypothesis would be that there's no association between gender and belief in afterlife. And then the alternative hypothesis is that there is an association. To test this using the Pearson's chi-square test statistic, I need to plug into the formula that we mentioned above. And the first thing I have to calculate are the expected frequency counts. So we're given the 4 observed frequency counts for each combination of gender and belief in afterlife. So female yes is observed to be 509, female and no is 116, male yes and male no counts we know as well. And now we need to calculate what would be the 4 corresponding expected frequency counts. So we need to calculate E11, which would be female and yes. So like I said above, the equation for that is going to be the corresponding row sum times the corresponding column sum divided by the total sum. So for E11, the row sum is 625, so that's the total sum of being female, regardless of your belief in the afterlife. Then the column sum is going to be 907, and that's believing yes in the afterlife, regardless of gender, divided by the total sum, which is 1127. And so that's the total sample size. So that would be the expected frequency count for female yes, and that's approximately equal to 502.99. And then I have to calculate that for the 3 other expected frequency counts. So E12, that's going to be equal to 220 times 625 divided by 1127. That's approximately equal to 122.01. Then if I do the same thing for E21, that's going to be approximately equal to 404.01. And E22, which would be male no, the expected frequency count for that is going to be 97.99. So once I have calculated the 4 expected frequency counts and given my 4 observed frequency counts, I'm now ready to calculate the chi-square test statistic. So the equation for that is as follows. Basically, for every cell that you observe, you're going to calculate observed minus expected squared divided by expected, and then you sum that up for each cell. So in this case, I have 4 observed counts, so I need to subtract and square the expected frequency counts from that, and then divide by expected, and sum each of those terms. So I'm going to sum 4 terms in total. So for this particular problem, the chi-square test statistic is going to be equal to 509 minus 502.99 squared divided by 502.99. So this is going to be observed, which is 509, minus expected, which is 502.99, squared, divided by expected, which is 502.99. So that's the first observation. For the second observation, it's going to be 116, which is the observed, minus the expected, which is 122.01 squared, divided by 122.01. The third sum is going to be 398 minus 404.01 squared divided by 404.01, and then the final term is going to be 104 minus 97.99 squared divided by 97.99. When I sum these 4 terms together, the final chi-square test statistic is going to be approximately 0.82. So I now have my chi-square test statistic, which is 0.82, and I need to compare that to a chi-squared critical value at alpha is equal to 0.05. And the degrees of freedom for my critical value is going to be equal to capital I minus 1 times j minus 1. So I and j refer to the number of factor levels in the 2 categorical variables. So in both cases, we have 2 factor levels for each variable. So that's going to be equal to 2 minus 1 times 2 minus 1, which is just equal to 1. 1. So I want to check the critical chi-squared value at alpha is equal to 0.05 and degrees of freedom is equal to 1. When I check that in R or in a critical value table, the critical value is 3.84. So our test statistic, 0.82, is less than our critical value, 3.84. So at alpha is equal to 0.05, we're going to fail to reject the null hypothesis. So at alpha is equal to 0.05, we fail to reject HO. And there is no statistically significant association between belief in afterlife and gender. And we are done with this problem.